You know, you're right.
My camera.
Normally, vision sensors are cameras. They're just, and it took us years to get this uh, because cameras, video is a lot of information. Basically, video consists of what's a pixel? I may know what a pixel is. Yeah, have y'all heard from pixel?
Like, there's one P, there's a P on this.
Well, it could be if it's a color pixel. The pixel stands for a picture element, by the way. Did I spell that right?
Picture.
No, that's a picture. That's not a picture. That's a picture. Somebody help me. PICTUR. A picture element. That's the
Picture.
yeah, picture pixel. This is hard to see. So basically, the way we do video is we do scans. So the way the cameras work is they basically scan from left to right, and then when they do a scan line, they come back and just scan from top to bottom. And basically, when we give what we call a pixel resolution, the first thing they give you is the number of pixels per line, and then they give you the number of lines. Now, are we talking about pixel resolutions? Like 1024 by 768, which means there's 1024 pixels in one line, and then there's 768 lines to develop that picture.
You just multiply those two.
You get the number of pixels. Yeah, if you multiply the two, you get the number of pixels that's required to display. And the problem we've had is that when we moved into computers, so on computers, basically we either turn them on or turn them off. And what we do is we pixel. And the next class, I'll bring my microscope over here so you can actually look at the screen and see pixels. Used to you could on a TV, the pixels were so big, you could literally take some spit and put it on, and just a spit you could see a pixel because the pixels were so big. Now the pixels are so small, and to do it, to do color, basically we have 3 prime colors. We actually have 4 prime colors. Anybody know what they are?
You got red, blue.
Yeah, red, blue, green, and what's the third one? Black. So if you notice my screen here, it's on a black background. So normally we put the pixels, we have a black background, and then we put the pixels on top of that, right? Understand? And so we don't actually display black. We display red, green, and blue, and then when we turn them off, we get white. We get black. Does that make sense? And then we can combine some TVs. Sony advertised it for a long time. They added a third element inside the pixel. They added yellow. You know, how many people could tell that? None. It's just like colors. You know, like my shirt. If I was to put my shirt in the sunlight and in here, it would actually look like it was different colors. So your brain does a lot of processing through it. So this is the primary still that TVs use. And you can actually see, if you probably can't where you're at, but I can see them, these little squares on inside here. So technically, a combination of 3, we refer to these as a triad, and they come different ways, by the way. And of course, I think it's a triad. We use groups of triads to make a pixel. So a lot of your computer screens gives you the ability to change your pixel resolution. Your TVs usually don't. The pixel resolution you get on your TVs are fixed. The ones on our computers, we can very easily go in and change the pixel resolution. And what we're doing is the bigger the pixels, we're just adding more triads inside the pixel. And so on computers and on TVs now, pixels are squares. And we just combine a number of triads inside that to get that. So what's so neat is that we're scanning from top of, we got a perfect scan. We're at the top. We go across, then we drop down, we scan. And by the way, the display, you can't see these. The TV, the display is what we call blank. They don't show you the return. They just show you the left to right scan, right? Does that make sense? And, so what I can do, if I know, and we're getting these images back off these cameras, that if something moves in here, then your camera would pick that and it would be giving you all this information, and then all of a sudden the information would change, right? You understand? And then when it went across here, it would give you information, said I'm going to do this color, and then all of a sudden the information would change. And then it would come over here and it would give you this image, and all of a sudden the information would change. So if I can come in here and read this information, then not only do we know where something's at, we also know how it's what? How it's oriented. Yeah. So so over there, a couple of our robots over there in the hall building has cameras on them. And what you do is you literally train the camera to recognize. You bring up an application. You train the camera to recognize a certain shape, which is neat. And then what you do is you say, you can tell it to recognize it over a certain rotation, you know, and then it develops all the image. But you have to put the image out there first, right? You understand? And it learns, the camera literally learns that image, which is pretty neat. So this is basically a sensor. We know about this, and this is what every one of our slides starts off with. So position, speed, weight. We haven't talked about count, pressure, flow rate, temperature, light, thickness. We didn't talk about. I might add this. This is a pretty interesting topic. Gas levels. I don't remember talking about gas levels. Orientation and shape, proximity. We didn't talk about moisture detectors and viscosity, which would be the thickness of liquids. So vision sensors. So this is what we just got through talking about. So basically the way the cameras do, and these send this to your TV. By the way, what we get is to keep everything in sync. So my camera's over here taking pictures. And then if my TV is not synchronized with the camera, y'all understand that, then this is going to cause all type of problems. So what the camera does, at the end of every horizontal line, it gives us a pulse. We call it horizontal sync. And then down here, when it hits the bottom, it gives us a vertical pulse. And so what this does is this camera generates these synchronization pulses. And as soon as this comes into your monitor, it automatically gets in what? In sync with the camera. In real old TVs, we actually had controls on our TV. The TV would start rolling, and you'd go, we called it vertical hold, and you'd have to adjust your TV a little bit to get back in what? To get back in sync. Horizontal, if it got a horizontal sync, the TV would lay over. And we had two controls on our TV. These are really old, and they wouldn't be compatible now, but we had to synchronize these. The problem is that the tuning circuits were made out of components that varied in temperature, capacitors and inductors. Now we use things called what we call phase-lock loops, and these guys, we don't have to worry about that. So I don't remember the last time I've seen a monitor go out of sync with the actual cameras themselves. Well, what we're talking about is now we've got this thing set up in some type of metrics, right? So our pixels would be what we call, these would be our horizontal metrics. And then the actual scan line would be the vertical. So what that means now is what I get back off my camera I can literally have a digital image of a digital representation of the object itself. We would even get back color, so it would give us back on the sensors, on the actual sensors that's in the camera. We have red, green, blue sensors in the camera, right? You understand? And one of them would pick out a little more, then it would give a little more output than the blue and the green. And so now not only could we detect the orientation, we could also detect what? Colors. We could actually detect colors with these cameras. And these would give us back a digital signal that not only represents the orientation, but represent the colors. Now, why did it take us so long to do this? There's so much information coming back off these cameras, because if you're doing 1024 by 768 resolution, and you're doing that at 16-bit color, which would give us 65,536 different colors, then you would have to have 16 bits. That would be 1 word of memory or 2 bytes of memory for every pixel on the screen. For every pixel on the screen. And that's a lot of memory. And you're trying to transfer that information from the camera into a computer that's trying to process that information. So the problem we had so long with these vision systems is we did not have the processing power in our computers to handle that much information. Now it's built into the camera. It's really neat. So what the camera will do now is once you train that camera, it'll send you an XY coordination. It'll say, this is XY. This is where this thing's located. XYZ coordination. It'll send that information back to the computer, and now the computer's only processing and instead of processing all the video, all it's trying to do is get these coordinate systems. It's what we call a Cartesian system back off the camera. And now that information is actually in the water, in the camera itself. So these cameras, the size of the processors that we have now and the speed that they operate, now these video systems are very, very popular. They're still not extremely cheap, but they're very, very popular. Because now what we can do, instead of us trying to put on our robot, trying to put everything at the same orientation, we have a camera up there and we send the information to the robot, and the robot does what? Orients itself to the item instead of trying to orient the item to the robot, which is really neat. So the processing power we have now makes this available, like even artificial intelligence. Artificial intelligence has been around a long time, but we just didn't have we didn't have the processing power to handle the growth, the magnitude of information we have to process for the machines to look like they learn. And this is 16-bit color, guys. This is 65,000. You know, you go to 32-bit color, and the problem is now our TVs do more than we need. Right now, it used to have a big screen TV, you had to set back away from that 10 feet. Now you can get up on your TVs, you can get what? You can get right up on them, and you still have a really, really sharp picture. But how many people stand this close to the TV? So the pixel resolutions we're using now is basically a waste of money. But people will still go out and buy those high resolution TVs. I mean, extremely high resolution TVs, and then they set 10 foot away from it, right?
4K, 8K.
Yeah, we have 4Ks, 8Ks, yeah. Yeah, they've stopped the rows and the colors. Those people didn't understand the 1024 by 768. So now what are they basically? They're telling you the number of pixels. So this is what we can do with these things now. Not only can we by the image or what we get back from the camera in this XY coordinate system, right? So still we're having problems. We can't tell depth with a single camera. But what are they doing now? They're adding cameras at 2 different angles, right? You understand? And now they can not only tell what, but comparing the 2 cameras, they can also now tell orientation, and they can also tell depth. I've never seen the dual camera situation, but I can understand how it works. So what we do now is, since we have this metrics, this row and column metrics, it's just like your touch screens, right? So your touch screens, that's all you got on your touch screens is you got rows and you got what? Columns. And when you come up here and touch, that's what you're doing. That's the way your phone knows where you're at. And normally we use what we call capacitive sensors. I think Alex also has a resistive sensor on yours because you got one that actually senses pressure, right? Yeah, I don't want to know how much you pay for it. Or you're still paying for it, right? It is paid for. Yeah, I got a iPhone 5S. How far am I behind? How many versions of that? But they're still updating it, so I'm happy. So it does everything I need. So this is the way the front of your display is set up like that. It's the same feature, right? You understand? So now, if I've got this set up in a row, if I got to set this thing in columns and rows, right? You understand? You come in, you touch your screen. It gives a pattern of your finger, right? You understand? And now your computer knows exactly where your finger's at, which is pretty neat. But we use primarily what they call a capacitive display. A lot of industry uses what they call a resistive.
What makes those go out?
Huh?
What makes the touchscreen?
Well, usually people, you think about the connections you have to make to it. And plus, if you break the screen, that's going to cause you a problem. This is why they have layers. I've seen phones that's got cracked screens and they still work because they hadn't got into the sensor. But if you think about the thousands of connections that we have to make out here, and you drop that phone, all it takes is just, well, some of them will, yeah. And we had a unit that we used to put up on the side of the screen that took the place of a touch screen before we got all these touch screens. And before we used it, we had to recalibrate. I haven't ever had to recalibrate my iPhone yet. Is it in there? Is it part of touchscreens? Yeah, HMI. I've seen those where you it brings up a pattern. It has plus, and you touch it and touch it and touch it, and especially like this. So I know I have a calibration for this on this computer. I can bring up a calibration and it does exactly the same thing. It's got each corner, I think one in the center you touch to calibrate it for that. So what we're talking about, and this is what we're talking about. So edge detection, like I said, the program that we used to have in the ADB, but we lost our operating system before we backed it up. So we could actually put all these blocks out in its range of motion, and it had letters on it, and we could orient them any way, and it would go out there and automatically orient itself, pick up the blocks that spelled robot. It was really cool. It'd come up and set them on the side. All you had to do is make sure that and the camera was up here. Now we had to calibrate that. We have to calibrate the camera. So what we have is a test pattern that we put down where we want it to vision in, and then we come in and calibrate that camera. So you're right, most of these cameras have to be calibrated. And then once you get it calibrated, then you just point it at whatever object you want it to learn, and then you come in and the camera literally memorizes that, and then for you. And then when it picks that object up, it would actually send an XYZ coordinates into the controller, and the robot just went to that spot. Sure did. But ours didn't. It was just a camera it's a camera mounted on the top that we had to put in a metal case. So guess what? One of the students jogged it up there and wiped our camera out. So now we got it inside a metal box. And that's it, guys. I mean, it's not that hard to understand, but you have to understand to process vision, it's going to take a lot of it, and these cameras are not cheap. So usually they protect them because they are not cheap, because now the cameras have tons of, these guys are microcomputers themselves. So like I said, can y'all see how that works? And y'all understand when they give that pixel resolution? Yeah. So that's about it on vision sensors. Vision sensors. What's usually on the camera? Anybody got any in there that y'all work with? Usually they have a focus on them it's still a manual focus.
Yeah, robotic camera sensors for our safety door cameras.
Yeah.
Have infrared cameras mounted on that gather and take numerous images of all the components and even just the movement of the door, unlocking and unlocking it has a tolerance range.
So they're in there for quality assurance. And these are becoming very popular. Robots are actually becoming very popular in quality assurance. But I still don't know any place where the human eye still won't come in there and do what? Still look them over. Because even though we've got all this neat stuff, we still need to come back and look. Even in cars, they still have somebody out there that looks at the paint job. So like we said, people say robots and automation is taking jobs away, but for our area, they've done what? Yep. They've added thousands of jobs. Because like I tell my people, used to, it was cheaper for these people to make their units overseas and then do what? Ship them over here. Now, because of automation, it's cheaper for them to do what? Make them here than it is to make them over there and ship them over there. So automation has helped our area out immensely. So guys, that's it. That's all the lectures for the entire term.
Yes.
Is that because we're over or because I did them so good?
Right.
You're clapping for me or And if you've seen any sensors out there that we haven't talked about, if you can get some information on them, we might add them to the course. But I don't know of any more that you told us.
Okay, so my roommate, he got a charger,
A what?
a charger pack for his phone. So what what's the cause of it?
Okay, what's required to induce an EMF?
Motion.
Got to have what?
Strength of the field.
A magnetic field.
And they got four.
And then we got what? So how does so all it is a transformer. So what you got is inside these units now, they got a bunch of coils inside your unit. And then when you come up here and you place that thing on there, it's generating a what? An AC field, couples through just like a transformer with an air core, not this. Generates an AC inside the unit. And these things are really neat. Nancy's got one on her truck. So she can charge her phone just by what? Setting it on there. So a lot of you use, and I've got a toothbrush. I got an electric toothbrush that uses the same principle. But it's just it's an air core transformer. So, but we're trying not to get a lot of energy, right? It still takes a pretty good time to charge them. But,
On your phone, on your Samsung.
yeah. Probably your phone, right? But it works. You got the inductive charger. I think you probably still got a charge jack you can use, right? Can you still a plug? You don't have a plug. You still got a plug on it, right? Yeah. These things are. But all it is just a transformer. So you got a bunch of coils inside your phone. It usually wraps around the outside like this. And then you step it down on the primary of the transformer. What does it do? It just induces the voltage into that. They rectify it and regulate it, and then you use that to charge those.
They got on some that do like reverse charging. Well, Samsung.
Yeah, I know. I've seen that where you can loan your phone. You can charge somebody else's. Yeah, I've seen that. So that would be neat.
I'd rather not.
So undoubtedly, this probably has an oscillator in it, and it just reverses the primary secondary. Yeah, it would be because that was one of the commercials where people say, but it's got to be a special phone. Y'all couldn't charge my iPhone 5S.
It came with a adapter to plug in. It's got USB.
Yeah, that's what I was asking.
Cool.
Yeah.
Mhm.
All right, guys.